Welcome to your theory video for the density lab. Let's start with density itself. Density is the property of a substance. It's given by the Greek letter rho, just defined as its total mass divided by its total volume. If the object has uniform mass density, then this gives the exact value for the density. If it is not uniform, then it's the average density. The units that are usually used in physics, our base units are kilograms and meters, so it's kilograms of mass divided by volume in cubic meters. Or, and you often see this in chemistry, mass in grams per cubic centimeter. So, for example, let's say I have a 25 kilogram object, and I've measured it to be 25.0 kilograms exactly, and it occupies a volume that is measured to be 0.30 cubic meters. The density is going to be 25.0 divided by 0.30. Two significant digits limit our answer, so it comes out to just be 83 with the combined unit of kilograms per meter cube. Similarly, if we had an object, let's say it was 52.3 grams, three significant figures here, and it occupied a volume of 8.05 centimeters cubed, then its density would be 52.3 divided by 8.05. That's three significant digits for the answer, which is 6.50, and the combined unit is grams per centimeter cube. Now, converting between the two, well, it's pretty straightforward, but the first thing we have to remember is that if we want to go between kilograms and grams, we remember this conversion. The definition of a kilogram is 1,000 grams. And we also need the conversion for the volume. So it's not obvious, but please trust me here. 1 cubic meter is actually 1,000,000, or 1 times 10 to the 6th cubic centimeters. So using these two conversions, we can go between values in kilogram per cubic meter to gram per cubic centimeter and vice versa. So let's convert our 83 kilograms per cubic meter into grams per cubic centimeter. So I take my original number, I multiply it by a conversion factor. I'm first going to convert the kilograms to grams. So if I have kilograms in the numerator, I want them in the denominator of my conversion factor. So 1 kilogram equals 1,000 grams. There's one conversion factor. The other one is going to convert cubic meters to cubic centimeters, because cubic meters in the denominator here, we want it in the numerator for cancellation purposes. 1 meter cubed is 1 times 10 to the 6th centimeter cube. So when we multiply all through, the kilograms up top here get canceled by the kilograms here. They cancel out to 1. The meter cube on the top gets canceled to 1 by the meter cube on the bottom. Let me cancel that. And we're left with grams per cubic centimeter. We just have to do the operation. 83 times 1,000, all divided by 1 times 10 to the 6th, or 1,000,000. Let's do the calculation then. right? So it's 83 times 1,000 divided by 1 times 10 to the 6th, and that gives us 0.083 grams per centimeter cube. To express it with more obvious two significant digits, I can put it into scientific notation, 8.3 times 10 to the minus 2, right? 1, 2 decimal places I moved over. Still grams per cubic centimeter. The other way around, we can do our example here. We have 6.50 grams per cubic centimeter. Our conversion factor, in this case, to go from grams to kilograms, well, grams in the numerator, I need grams in the denominator. So 1,000 grams. And then we have our 1 kilogram. And then we want to convert centimeter cube to meter cube. Centimeter cube is in the denominator, so I want it to cancel out here. 1 times 10 to the 6th centimeter cube, right? All coming from this conversion factor, divided by 1 meter cube. Okay, so 6.5 times 1 times 1 times 10 to the 6th, all divided by 1,000, is pretty much going to give me 6.5 times 1,000, or 6,500 kilograms per cubic meter. Again, in more appropriate scientific notation, to see that we really only have 3 sig figs, it's 6.50, 1, 2, 3 times 10 to the 3rd kilograms per meter cube. And so basically what you can see is as I go from kilograms per cubic meter to grams per centimeter, I basically divide by 1,000 or multiply by 0.001. So to wrap it up, to summarize conversions back and forth, for your kilogram per cubic meter to gram per cubic centimeter, you multiply by your conversion factor, essentially of 0.001 kilograms per meter cube, grams per centimeter cube per kilogram per meter cube. So if I multiply 83 kilogram per meter cube by this, kilogram per meter cube cancels out, and I'll get my 0.083 gram per centimeter. Vice versa, if I want to go from grams per cubic centimeter to kilograms per cubic meter, then my conversion factor is 1,000. 1,000 kilogram per cubic meter per every gram per cubic centimeter. And so if we start off with 6.50 gram per centimeter cube, multiply it by 1,000, we'll get our 6,500, we'll get the cancellation of gram per centimeter cube and be left with kilogram per meter cube. So those are quick and dirty ways to convert between the two different units of density. Okay, so quickly, specific gravity. It really is just as you would read in the experiment file, equal to the density of your material divided by the density of water. So really it's sort of basically comparing the density of your material in question to the density of water. Pretty straightforward. The density of water, H2O, is basically 1 gram per centimeter cube. And if you do the conversion, it's 1,000 kilograms per meter cube. All right, so depending upon the units you're given the density of your material in, you'll divide it by the density of water in the similar units, right? There is no unit for this because it's the quotient of two like units. They'll cancel out. And the idea of specific gravity is essentially a number that tells you how many times, what factor your density is compared to water. If your specific gravity is 1, that means your material is water. If your specific gravity is 100, that means your material is 100 times denser than water. If your specific gravity is 0.1, then your material is 0.1 times the density of water, or 1/10. Moving on, you will be measuring the mass m of same material objects and you'll be knowing their volumes. We can find a good value for the density by plotting the mass values, and we'll do it in grams here, versus the volume in cubic centimeters of the objects. If they all have the same density, if they all are of the same material, they all have the same density. And the idea here is we take the density definition, mass per volume, we rearrange it, multiply by V on both sides. We find that our mass is equal to the density times the volume. If you graph it with mass on the vertical, compare it to the point slope form of a line, y versus x, you're going to get, for 5 different objects, approximately 5 data points that should form a line. And let's just guess the line looks something like this. Right? And by looking at it, you should see that the slope is the density. Right? So the slope of the line is equal to the density. If you did it in mass in grams, volume in centimeter cube, then the units are grams per centimeter cube. And so you're going to, for 3 different materials, measure the mass, measure the volume of 5 different objects made of that same material. You're going to form a line. You're going to use a best fit line, and you're going to generate the equation for that best fit line. It's going to look something like this, where you know the value of m and b. B should be 0, meaning it should go through the origin, but that's not a data point necessarily. So the slope equals the density. And so once you get the equation for your line, look where the slope's supposed to be. That number is your density, in this case grams per centimeter cube. That ends the theory section of this video.